2,900 degrees Fahrenheit. That is the temperature of liquid steel. Not hot enough to melt stone, not hot enough to vaporize iron, but more than sufficient to reduce a human body to carbon residue in under 4 seconds. Now hold that number. Because in 1901, men stood 20 feet from that temperature, every single day, for 12 hours. With no heat-resistant suits, no automated monitoring systems, no thermal sensors, no emergency shutoffs, and no union contract that guaranteed their family would be compensated if something went wrong. They stood there because the job paid $1.25 a day, and the mill needed them there. This is the story of the open-hearth steel mill, the machine to process the environment and the industry it constructed from nothing. It built American cities. It armed 2 world wars. It produced the structural steel that holds your city's skyline in place right now. It also killed men by the hundreds, and it did so through a combination of physical forces that were, in many cases, completely understood by the engineers who designed the furnaces. The machine was not reckless. It was precise. It was the conditions around it that were lethal. Let's start with the scale. A full-scale, open-hearth steel mill in operation during the early 1900s occupied a building roughly the size of 8 football fields laid end to end, not including the ore yards, the coke ovens, the slag pits, or the rail lines running in and out, just the main building. The open hearth furnaces themselves, the primary heat chambers, were typically between 80 and 120 feet long. Each furnace had a working depth of roughly 30 feet and a roof height above the bath of 15 to 20 feet. The steel bath inside, the pool of molten metal, could hold anywhere from 50 to 400 tons per heat cycle, depending on the size of the furnace and the era. 400 tons, that is the weight of 267 standard automobiles, held in a liquid state, at 2,900 degrees, inside a structure made of brick, steel, and refractory ceramic lining. A large integrated steel plant of the Carnegie era, late 1890s through 1910s, might run 15 to 20 of these furnaces simultaneously, side by side, in a single building. The noise level inside that building has been described in period accounts as physically painful after 30 minutes. There were no ear protection standards. Workers developed significant hearing loss within a few years of continuous service. The radiant heat from an operating furnace, standing at a safe observation distance, has been measured in later industrial studies at temperatures sufficient to cause first-degree skin burns within minutes of unprotected exposure. Now consider the men charging the furnace, the workers who loaded raw materials directly into the open chamber, worked within 8 to 12 feet of the open door. Let that settle for a moment. 8 feet. Before we explain the furnace, we need to explain what it was built to replace and what problem it solved. Because the open hearth mill didn't appear from nowhere, it was a technical response to an engineering bottleneck that was slowing down the entire industrialization of the United States. In the 1860s and 1870s, the dominant method of producing steel in the United States was the Bessemer process. The Bessemer converter was a pear-shaped vessel, typically 15 to 20 feet tall, that could be tilted on a horizontal axis. You loaded it with molten pig iron from the blast furnace. Then you blew compressed air through the bottom. The oxygen in the air reacted with the carbon in the iron, burning it off and generating enormous heat. The process took roughly 15 to 20 minutes. Fast, efficient, relatively cheap. But the Bessemer process had a critical flaw. It could not remove phosphorus or sulfur from the iron charge. If your ore contained significant amounts of either element, and much American ore did, your Bessemer steel was brittle. It fractured under stress. It was acceptable for rails, but inadequate for structural beams, armor plate, or high-tension applications. There was also no precise control over carbon content during the blow. The process moved too fast. By the time you detected a problem, the heat was already done. The open hearth furnace solved both of these problems. The open hearth process allowed the furnace operator to monitor and sample the steel bath throughout the heat. You could add materials to adjust chemistry. You could remove phosphorus through slag formation. You could control the carbon level with a degree of precision the Bessemer process could not match. The heat cycle was slower, between 6 and 12 hours per batch compared to the Bessemer's 20 minutes. But what came out was a more consistent, more reliable product. And here is the economic reason this mattered. In 1880, the United States was in the middle of the largest infrastructure expansion in its history. Railroads needed hundreds of thousands of tons of rail steel per year. cities needed structural steel for buildings that were beginning to reach heights previously considered architecturally impossible. The Brooklyn Bridge, completed in 1883, required wire rope steel of exceptional tensile strength. The skyscrapers being designed in Chicago and New York through the 1880s and 1890s needed steel that could carry compressive and tensile loads simultaneously without cracking. Bessemer steel was not consistently reliable enough for those applications. The open hearth furnace was. By 1900, open hearth steel production in the United States had already overtaken Bessemer. By 1910, open hearth dominated. By 1920, Bessemer was nearly gone from American production. Now let's talk about what actually happened inside one of these furnaces. The open hearth furnace is a regenerative furnace. That word, regenerative, is important. It is the core engineering principle that made the process work. Here is the basic structure. The furnace is a long, low chamber, rectangular. The roof is a shallow arch of refractory brick, curved to reflect heat downward onto the steel bath. The floor of the furnace, called the hearth, is also lined with refractory brick, typically a material called magnesite or dolomite. The steel bath sits on this hearth. At each end of the furnace is a port, an opening through which fuel and air enter. Underneath each port is a large chamber called a regenerator, also called a checker chamber. These chambers are filled with a stacked lattice of refractory brick. Here is the cycle. Fuel, gas. In early mills, this was producer gas derived from coke, later natural gas, and preheated air enter through one port. They mix and combust in the furnace chamber above the steel bath. The flame passes over the bath, heating it. The exhaust gases then exit through the opposite port and pass down through the opposite regenerator. The heat from those exhaust gases is absorbed by the brick lattice in that regenerator. After roughly 20 minutes, the direction of the flame reverses. Now the gas and air enter through the port that was previously exhausting. As the incoming air passes through the regenerator that was just heated by exhaust, it picks up that stored heat and arrives at the furnace already preheated, sometimes to temperatures above 1000 degrees Celsius before it even contacts the fuel. This is the regenerative principle. By preheating the incoming air, you dramatically increase combustion temperature inside the furnace without requiring more fuel. The system is recovering and reusing its own waste heat. William Siemens patented the core principle in the 1850s. Pierre-Émile Martin adapted it specifically to steelmaking in France in 1864. The result was a furnace that could sustain temperatures of 1600 to 1700 degrees Celsius continuously, hot enough to melt iron and maintain a liquid steel bath. Now, the charge. At the start of a heat cycle, the furnace is loaded. The charging process varied by mill and era, but typically included pig iron, either molten, delivered directly from the blast furnace in torpedo cars, or solid, in the form of cold pigs loaded by crane. Steel scrap, the mill's own internal scrap, or purchase scrap from external sources. Iron ore, added to the bath to supply oxygen for carbon removal. Limestone, added as a fluxing agent to help form slag. Limestone does something specific. When heated, it breaks down into calcium oxide and carbon dioxide. The calcium oxide reacts with phosphorus and other impurities in the steel, pulling them out of the metal and into a floating slag layer on top of the bath. The slag is the waste product. It floats on the liquid steel, lighter than the metal. It is periodically removed by pushing it out through openings at the side of the furnace. Now the heat begins. Over the course of 6 to 12 hours, the temperature in the furnace steadily brings the charge to full melt. Operators take samples by plunging a small metal rod into the bath, quickly withdrawing a solidified sample and sending it to an adjacent laboratory for chemical analysis. They are checking carbon content, phosphorus, sulfur, manganese, silicon. When the chemistry is correct, when the steel meets specification, the heat is ready to tap. Tapping means opening the taffel at the bottom of the furnace. A stopper bar is withdrawn and the liquid steel pours out through a channel into a ladle, a large steel vessel lined with refractory brick hanging from an overhead crane. The ladle might hold 100 to 300 tons of liquid steel. From the ladle, the steel is poured into ingot molds. These are cast iron molds, typically 3 to 5 feet tall, that shape the steel into rectangular blocks as it solidifies. The ingots are then stripped from the molds and moved, still hot, into a soaking pit, where their temperature is equalized throughout, and then to the rolling mill, where they are worked into plates, beams, rails, rods, or other shapes. That is the complete cycle. Fire to steel. 12 hours. Repeat. Now here's the part that gets complicated. That entire process, every stage of it, was performed by men using manual tools, physical labor, and sensory judgment. There were no electronic temperature sensors in most early 1900s mills. Temperature was assessed by the furnace operator observing the color of the flame and the bath. Different temperatures produce different light colors: dark red, bright red, orange, yellow, white. An experienced operator could read furnace temperature to within roughly 50 degrees Celsius by eye. That skill took years to develop, and the operator stood in front of a furnace producing radiant heat at levels that required periodic retreat just to continue functioning. This is the work environment. Let's go there now. The great steel mill districts of early 20th century America were concentrated in western Pennsylvania, eastern Ohio, and the southern shore of Lake Michigan. Pittsburgh, Homestead, Braddock, Youngstown, Cleveland, Gary. These were not incidentally industrial places. They were built around the mills. The city existed because the mill existed. The geography was chosen for specific logistical reasons. Iron ore came by ship from the Lake Superior Ranges, the Mesabi Range in Minnesota, the Marquette Range in Michigan. Coal came by rail from the Appalachian coal fields of Pennsylvania and West Virginia. The rivers, the Monongahela, the Allegheny, the Ohio, provided water for mill operations and transportation for finished goods. The mills ran continuously, 24 hours a day, 7 days a week, 365 days a year. The only shutdowns were for major maintenance, equipment failure, or market collapse. Inside the mill, the ambient temperature inside an operating open hearth building, not near the furnace, just standing in the middle of the floor, ranged from 90 to 120 degrees Fahrenheit on the moderate day. In summer, with exterior temperatures in the 80s and 90s, interior temperatures in the active work areas could exceed 140 degrees Fahrenheit. The humidity was variable. The process produced significant amounts of steam and combustion exhaust. The air was not clean. Carbon monoxide was present at measurable levels in areas near the furnace doors. Iron oxide particles were airborne throughout the building. The light was a combination of harsh overhead industrial fixtures, the ambient orange glow of heated metal, and periodic blinding flashes of white light from the furnace interior when doors were opened. The noise was layered, low-frequency vibration from the regenerator burners, the mechanical rhythm of overhead cranes, the trolley wheels, the hoist motors, the impact sound of metal striking metal throughout the building, the intermittent roar of combustion when a furnace door opened and the heat wave expanded outward, the sound of the ladle filling during a tap, a sound described in period accounts as a continuous roar, like standing next to a waterfall made of fire. The smell was iron oxide, sulfur compounds, coke gas, and lubricating oil burning off hot metal surfaces. Workers on the furnace floor had 2 15-minute breaks and a 12-hour shift. They ate in the mill, not in a cafeteria, in many early mills, but beside their workstations. Heat exhaustion was common in summer. It was treated by having the workers sit down for a few minutes and then return to the floor. There was no air conditioning. There was no mechanical ventilation in many early mill buildings. The roof had monitor windows that could be cranked open to allow hot air to rise and exit. But the relief was marginal. This is where they worked. Now let's talk about what happened when things went wrong. Here's the problem with steel mill accidents in the early 1900s. Most of them were not dramatic. Most of them were not explosions or catastrophic failures. They were incremental. A man slipped on a wet floor and fell into the path of a ladle crane. A charging car moved without warning while a man was adjusting the track. A tap opened before the ladle was properly positioned. The mill killed people through a combination of scale, temperature, speed, and proximity. Let's go through the specific failure modes: boiler and furnace explosions. The regenerative chambers of an open hearth furnace were not pressurized like a steam boiler. The furnace itself operated at roughly atmospheric pressure, but the adjacent equipment, the steam boilers that powered the cranes, the blowers, the casting machines, operated at pressures between 150 and 250 psi. 150 psi. That is enough pressure to drive a piston through a cast iron cylinder. If a boiler failed, from scale buildup, metal fatigue, low water level, or operator error, it did not leak. It detonated. A steam boiler explosion at 200 psi is not a pressure release. It is a rapid phase transition. The water inside flashes to steam instantaneously. The volume expansion ratio of water to steam at atmospheric pressure is approximately 15,700 to 1 In an enclosed vessel at pressure, the failure mode is mechanical rupture propagating faster than the speed of sound through the metal shell. Early 1900s boiler explosions were not rare industrial events, they were routine. The National Board of Boiler and Pressure Vessel Inspectors, founded in 1919, estimated that in the years before standardized inspection, the United States experienced approximately 1,400 boiler explosions per year across all industries, 1,400 per year. In steel mills specifically, the hazard was compounded by the proximity of pressurized systems to furnaces, molten metal, and large numbers of workers in a confined space. Molten metal incidents. The most common serious injury category in open hearth operations was contact with molten steel or slag. Here's the physics. Liquid steel at 2,900 degrees Fahrenheit has a density of approximately 6.9 grams per cubic centimeter. It is heavier than water. When it contacts a cool surface, concrete, damp, refractory brick, a thin metal floor plate, the result depends on what that surface contains. If the surface contains trapped moisture, water in concrete, wet sand, a crack in refractory brick that has allowed moisture infiltration, the liquid steel causes an instantaneous steam explosion. This is called a steam explosion or a runout explosion. The water vaporizes faster than the steam can escape. The pressure is released through the path of least resistance, which is often upward, through the liquid steel. The result is a violent eruption of molten metal droplets thrown outward in all directions. The droplet size ranges from fine mist to chunks the size of a fist. At those temperatures, the droplet does not need to penetrate clothing or skin to cause injury. The radiant heat from a droplet passing within 3 feet of exposed skin is sufficient to cause second-degree burns. If it contacts skin directly, the damage is immediate and complete. This type of explosion was responsible for a significant percentage of steel mill fatalities. It was caused by a combination of factors: moisture in the environment, aging refractory linings developing small cracks, inadequate inspection schedules, and the physical difficulty of fully drying and inspecting a furnace that was in near continuous operation. Crane failures. The overhead cranes in an open hearth building were the circulatory system of the operation. Without them, nothing moved. The ladles hung from cranes. The charging equipment was crane-driven. The ingot molds were moved by crane. A standard ladle crane in a large open hearth mill carried loads of 100 to 300 tons. The hook, the cable, the trolley, the bridge, everything in that system was under continuous dynamic load in a high-temperature environment. Early crane cables were steel wire rope fatigues. The individual wires developed small cracks from repeated bending over sheaves and drums. In a high-heat environment, the fatigue rate increases. Inspection required the crane to be taken out of service, difficult in a mill running on production pressure. If a ladle cable failed at full load, carrying 200 tons of liquid steel at 30 feet of elevation, the result was total. There were no secondary retention systems in early cranes. There was no hydraulic brake backup. There was a single mechanical brake, operated by the crane operator, who sat in a cab attached to the crane bridge. The period accounts of ladle drops in early steel mills are in the industrial safety literature. They do not require dramatization. The physics explains the outcome. Carbon monoxide. An open hearth furnace operating on producer gas generated carbon monoxide as both a fuel component and a combustion byproduct. CO is odorless. It is colorless. It binds to hemoglobin with an affinity approximately 250 times greater than oxygen. In an enclosed mill building with multiple furnaces, CO levels could rise in localized areas, particularly in lower zones, pits, and subfloor mechanical spaces, without any visible indication. Workers in early mills had no personal CO detectors. Canaries were used in mine shafts. In steel mills, the first indication was often a worker becoming dizzy or losing consciousness. A man who lost consciousness in an open hearth mill in 1905 was not in a safe location. He was on a floor covered with hot metal, moving machinery, overhead crane traffic, and radiant heat. Structural fatigue. The furnace buildings themselves were large, lightly enclosed structures. The roof and walls were primarily steel framing with corrugated metal cladding or brick panels. The overhead crane rails were bolted to the building structure. Decades of vibration from crane operations, Thermal cycling and the constant loading and unloading of massive weights produced structural fatigue. Column connections cracked. Crane rail fasteners worked loose. In several documented cases, crane rail failures caused derailments that sent loaded ladles in uncontrolled directions along the crane bridge. This is where it gets dangerous, and it stays dangerous for the entire operating life of the equipment. Now imagine doing that for 12 hours. The workforce of a large open-hearth steel mill in the early 1900s was stratified by skill, national origin, and seniority in a way that was extremely rigid. At the top of the furnace floor hierarchy was the melter foreman. He was responsible for all furnaces in his section. He managed the heat schedule, the charge composition, the sampling schedule, and the tapping decisions. He did not work a furnace directly, but he made the technical decisions that determined the quality of the steel and the safety of the crew. A good melter foreman could read a furnace by looking at it for 30 seconds. Below him was the first helper, also called the melter or the first melter. He was directly responsible for one or two furnaces. He managed the charging, monitored the heat, observed the bath chemistry, and directed his crew. This was a skilled position that typically required 5 to 10 years of floor experience before a man was considered fully capable. Below the first helper was the second helper. He handled the more physical aspects of the work, opening furnace doors, sampling the bath, managing the slag door. He was learning the first helper's job. Below that, the third helper, the charger machine operator, the stockhouse crew, the crane operators, the pit workers. The lower positions were frequently filled by recent immigrants. In the Pittsburgh district in particular, the labor force was heavily drawn from Southern and Eastern Europe, Hungary, Poland, Slovakia, Croatia, Italy. These men arrived with no English, no industrial experience, and no transferable credentials. They were assigned to the hardest, hottest, most physically demanding jobs on the floor, because those jobs required strength and endurance more than technical knowledge, and because the men who held the technical knowledge, the first helpers and melter foremen, were typically native-born or earlier generation immigrants who had worked their way up over decades. Pay scale in a representative 1905 Pittsburgh mill. Third helper / laborer, approximately $1.25 to $1.50 per day. Second helper, approximately $2 to $2.50 per day. First helper, $3 to $4.01 per hour. Melter foreman, $4 to $6 and per day plus performance incentives. The standard shift length was 12 hours, 6 days per week, 1 day off Sunday. Twice a year, when shifts rotated, a worker would work a long turn 24 consecutive hours to transition between the day and night shift schedule. The long turn, 24 hours, in an open hearth mill, standing beside a furnace. This was not an emergency measure. It was standard scheduling practice at U.S. Steel and most major producers until 1923, when significant public pressure and a presidential commission finally produced an industry agreement to move to 8-hour shifts. The shift structure changed. The work did not. Fatality rates in early steel mill operations are difficult to calculate with precision because reporting was inconsistent. The best available historical data, drawn from Pennsylvania Department of Labor records in early U.S. Steel internal reports, suggests that in the first decade of the 20th century, the rate of fatal injuries in integrated steel production was between 2.5 and 3.5 deaths per 1,000 workers per year. In a mill employing 10,000 workers, and several Carnegie-era plants reached that scale, that is 25 to 35 fatal injuries per year. Every year. Not a crisis. A baseline. The workers gave the furnace positions names. The first helper's position directly in front of the furnace door was called the hot side. The platform behind the furnace, where the regenerator controls were, was called the cool side, though cool was a relative term. The pit beneath the floor, where the tap channel ran, was called the hole. Pit workers were called hole men. The crane operators were called cranemen. They occupied an elevated cab and had one of the more technically demanding jobs in the mill. They were responsible for precise positioning of loads measured in hundreds of tons at height. Over men working on the floor below, a good craneman was valued, not by salary. Salaries were set by grade. By the fact that when a good craneman was running the hook, the floor crew paid slightly less attention to the overhead. That was the distinction. The open hearth furnace was not a machine you built and then operated indefinitely. It was a machine you built, operated until it degraded, and then rebuilt. The limiting component was the refractory lining. Refractory brick is ceramics engineered to withstand extreme temperatures. In an open hearth furnace, the floor of the furnace where the steel bath rested, was lined with magnesite or dolomite brick, materials that could withstand the chemical interaction between liquid steel, slag, and the lining surface. But no refractory lining withstands that environment indefinitely. The slag attacks the lining chemically. The thermal cycling, heating to 1,650 degrees and then cooling during shutdown, induces cracking and spalling as the brick expands and contracts. The mechanical impact of charging solid scrap damages the surface. The tapping of liquid steel through the tap hole erodes the area around that opening with every heat. A furnace hearth in continuous operation typically required relining every 200 to 400 heats, depending on furnace design, operating practice, and the quality of the refractory brick. At 6 to 12 hours per heat, that is roughly 2,000 to 5,000 hours of operating time. Relining required a complete furnace shutdown. The furnace had to cool from operating temperature to safe working temperature, a process that took 2 to 4 days. Workers then entered the furnace chamber to remove the worn lining material and install new brick. Working inside a furnace that is recently operated at 1,650 degrees Celsius, even after cooling, is not comfortable. Residual heat in the massive brick structure keeps the interior elevated for extended periods. The work was confined, dusty, and performed with hand tools in a structure designed for fire rather than human access. The regenerator checker brick also required periodic inspection and replacement. The checker chambers, those large brick lattice structures that stored and transferred heat, became clogged with dust, scale, and condensed combustion products over time. If the checker chambers lost efficiency, the furnace could not maintain the required combustion temperatures, and steel quality deteriorated. Inspecting the checker chambers required sending a man into a chamber that had recently been conducting exhaust gases at over 1,000 degrees Celsius. Cooling time was required. The space was confined, the surfaces were irregular, and the brick dust was a long-term respiratory hazard. Here is the engineering paradox. The furnace was most efficient and most profitable when running continuously. Every shutdown cost money and lost production, but the furnace degraded continuously through use. Running it longer between maintenance intervals maximized short-term output and increased the probability of catastrophic lining failure. Lining failure, a full breakthrough where liquid steel breached the hearth and flowed out of the furnace structure, was not a minor maintenance problem. It was an emergency. Liquid steel contacting the subfloor structures, the steel building columns, the adjacent equipment at 2,900 degrees produced consequences that moved faster than a man could run. This is the engineering reality that production managers in early 1900s mills operated in every day. They were making decisions about maintenance intervals with incomplete information about lining condition, under production pressure, with manual inspection tools. The furnaces were also giants that were, structurally, quite fragile in specific ways. The taphole, that small opening at the base of the furnace through which liquid steel was released, was lined with refractory material and was the single most thermally and chemically stressed point in the furnace. Taphole lining wear was unpredictable. An unexpected taphole failure during a heat, before the ladle was in position, was an uncontrolled release of liquid steel. There was no valve to close. There was no shutoff. The steel flowed until it stopped flowing. Between 1900 and 1920, the United States produced more steel than any other nation on Earth. That position was built almost entirely on open hearth technology. The numbers: in 1900, the United States produced approximately 11.2 million tons of steel. By 1910, that figure had reached 28.3 million tons. By 1916, as war demand accelerated, it exceeded 43 million tons. The majority of that production came from open hearth furnaces. What did that steel become? Railroad expansion in the United States between 1880 and 1920 required rail steel in quantities that were, in contemporary terms, staggering. A single mile of standard gauge track requires approximately 200 tons of steel rail, not including the structural steel in bridges, tunnels, and station buildings. By 1916, the United States had approximately 254,000 miles of railroad track in service. The steel required to build and maintain that network, replacing worn rails, expanding lines, rebuilding failed bridges, was continuous and enormous. open-hearth steel was the material of choice for heavy rail applications because its consistent chemistry and controlled carbon content produced rails with predictable wear characteristics. Bessemer rail had served in the 1870s and 1880s. Open-hearth rail was measurably more durable. Skyscrapers, the structural steel that made the American skyscraper possible, was open-hearth steel. The specific product was the wide flange beam, a rolled steel section with a cross-section shaped like the letter H, designed to carry both compressive and bending loads with high efficiency. Wide flange beams allowed building designers to create tall structures with floor spans far exceeding what masonry construction could achieve. The Empire State Building, constructed in 1930 to 1931, used approximately 60,000 tons of structural steel. The Chrysler Building, completed in 1930, used roughly 20,000 tons. The structural steel in the buildings constructed in the 1920s American building boom was overwhelmingly produced in open-hearth furnaces in Pittsburgh, Gary, and Youngstown. Every major American city built between 1900 and 1950 was built with open-hearth steel. The bridges, the buildings, the underground infrastructure, the water mains, the elevated rail lines, all of it. War production. During the First World War, American steel production pivoted substantially toward war materials. Armor plate for warships and artillery pieces. Shell casings, millions of them. Structural steel for shipbuilding. Locomotive steel for military railroad operations in Europe. The United States produced approximately 4.5 million tons of pig iron for military applications between 1917 and 1918. The open-hearth furnaces ran without shutdown. Operating schedules compressed, heat cycles accelerated to the limit of what the equipment could sustain. The same pattern repeated in World War II on a larger scale. By 1944, American steel production had reached 89 million tons per year. Tanks, naval vessels, aircraft structural components, artillery, ammunition, bridging equipment. The material output of American industrial capacity in World War II was built on steel, and the steel came primarily from open-hearth furnaces. The Sherman tank contained approximately 75 tons of steel in its hull, turret, and running gear combined. American industry produced approximately 49,000 Sherman tanks during the war, that is 3.7 million tons of steel, for one tank type. Urban infrastructure, beyond the visible buildings, the city infrastructure built between 1900 and 1950 was steel-dependent in ways that are now largely invisible. Water and sewer mains, gas distribution pipes, electrical conduit, bridge structures, retaining walls, rail yards, industrial facilities. The physical skeleton of the modern American city, assembled underground and above ground in the first half of the 20th century, was fabricated from open-hearth steel. The economic multiplication from steel output to city construction is not easy to quantify precisely. But consider this. The cost of structural steel per ton in 1905 was approximately $28. The cost of constructing the equivalent building structure in wood, masonry, or pre-steel alternatives was several times higher, and the resulting structure could not achieve comparable height or load capacity. Steel made tall buildings economically feasible. Tall buildings made high-density urban land use economically viable. High-density urban land use produced the concentrated economic activity that characterized American city growth in the 20th century. The open-hearth furnace sits at the beginning of that chain. Open-hearth steel production in the United States peaked in the early 1950s. At peak capacity, the United States had approximately 600 open-hearth furnaces in operation. They were producing roughly 80 to 90% of total national steel output. The mills at Pittsburgh, Gary, Cleveland, and Buffalo were among the largest industrial facilities ever operated on Earth in terms of physical scale and continuous output. Then the replacement technologies arrived, not all at once, incrementally, over roughly 2 decades. The basic oxygen furnace, the BU-OFF, was developed in Austria in the late 1940s and reached American production in the mid-1950s. It was a converter process similar in concept to the old Bessemer vessel, but instead of blowing air through the bottom, it blew pure oxygen through a water-cooled lance inserted from the top. Pure oxygen, rather than air, eliminated the nitrogen problem that had made the Bessemer process produce brittle steel. And pure oxygen accelerated the refining reactions so dramatically that a BOF heat took approximately 40 minutes compared to 6 to 12 hours for open hearth. That is not a modest improvement. That is a process operating roughly 10 to 15 times faster. A single BOF vessel could replace multiple open hearth furnaces in terms of annual output. The capital cost of a BOF installation was lower than the equivalent open hearth capacity. The operating cost per ton was significantly lower. Open hearth could not compete on economics. The physics of the process did not allow it. Electric arc furnaces, the electric arc furnace, the EAF, had existed since the late 1800s and was used for specialty steels throughout the first half of the 20th century. In the 1960s and 1970s, as the economics of scrap steel improved and electrical power became more accessible, the EAF became viable for commodity steel production. The EAF uses high current electrical arcs between large graphite electrodes to melt a charge of scrap steel. No blast furnace is required. No coke ovens are required. The EAF is a simpler, more flexible, more rapidly controllable process than either open hearth or BOF. The EAF does not require a steel-making complex of the scale that the integrated open hearth mill represented. A smaller facility, a mini-mill, could produce specific steel products competitively using local scrap and electrical power. By the 1970s and 1980s, EAF mini-mills were taking market share from integrated steel producers in specific product categories. They were faster to build, less capital-intensive to operate, and more responsive to market demand. What happened to open hearth US? Open hearth furnaces were progressively decommissioned through the 1960s and 1970s. The last open hearth steel production in the United States ended in 1991, from peak dominance in 1950 to complete elimination in 1991. This was not a collapse, it was an orderly technological replacement. Each furnace that was shut down was replaced, in the same mill or elsewhere, by BOF or EAF capacity that was more efficient in every measurable parameter. The engineers and managers who made these decisions were not abandoning the past out of sentiment or fashion. They were responding to straightforward production economics. Open hearth could not produce steel at a cost competitive with BOF or EAF. Maintaining equipment that was increasingly expensive to operate on a process that was slower than alternatives did not make economic sense. The furnaces came down. The buildings were cleared. Some mill sites were demolished entirely. Others were redeveloped. A few became industrial heritage sites. The process was gone. The capacity it represented had been redistributed to more efficient technology. Cut to modern steel mill interior. Clean, automated, EAF operation. Cut to crawler excavator working a construction site. Cut to skyscraper under construction. Cut to military tracked vehicle. The open hearth furnace did not disappear without leaving something behind. Its influence on industrial practice, equipment design, and manufacturing methodology carried forward in ways that are visible in modern industry. Refractory engineering. The refractory materials science developed for open hearth furnaces, the magnesite linings, the dolomite hearths, the silica roof bricks, provided the engineering foundation for modern high-temperature industrial processes. The BOF vessels that replaced open hearth use similar refractory materials. Modern electric arc furnaces use magnesite carbon brick in their sidewalls. Industrial kilns, glass furnaces, and aluminum smelters all operate on refractory principles that were substantially developed and refined in the open hearth era. Regenerative heat recovery, the regenerative principle, storing waste heat in brick checker chambers and using it to preheat incoming combustion air, was not discarded when open hearth ended. It was generalized. Modern regenerative thermal oxidizers in industrial plants use the same principle to destroy volatile organic compounds while recovering heat. Glass furnace regenerators are direct descendants of the open hearth checker chamber. Industrial process heat recovery in general, a critical component of modern manufacturing efficiency, was substantially advanced by the engineering work done on open hearth regenerator design over 70 years of operation. Ladle metallurgy, the practice of treating steel in the ladle, after it left the furnace but before it was cast, was developed and refined in the open hearth era. The ladle is not a passive transport vessel. It became, through the late open hearth period, an active processing vessel where final chemistry adjustments, deoxidation, and desulfurization were performed. Ladle metallurgy, the controlled processing of steel in the transfer ladle, is now a standard feature of every modern steelmaking operation. EF and BOF shops both use ladle furnaces, ladle degassers, and wire injection systems to refine steel chemistry after the primary process. The conceptual basis for treating the ladle as part of the metallurgical process came from open hearth practice. Overhead crane technology. The overhead bridge cranes developed for open hearth service, the 200-ton, 300-ton capacity systems required to handle ladles of liquid steel, drove significant advances in crane engineering, the electrical systems, the braking technology, the structural design of bridge cranes capable of handling dynamic loads of that magnitude. All of this was substantially developed in response to the demands of open hearth mill operation. Modern overhead cranes and steel plants, automotive stamping shops, heavy equipment manufacturing, and shipyards are direct descendants of the open hearth ladle crane. The mechanical principles are the same. The engineering has simply been refined. Industrial safety standards. The open hearth era produced the first systematic industrial safety engineering in the United States. Not from humanitarian impulse alone, from economic necessity. The cost of fatal accidents, equipment damage, production shutdowns, and worker replacement was measurable. Reducing that cost was economically rational. The National Safety Council was founded in 1913. OSHA's founding principles were, in many cases, derived from documented failure modes in industries like steel and mining. The accident investigation methodology now standard in industrial safety, identifying the contributing factors, the systemic conditions. The equipment states that combined to produce an accident was developed through the painful documentation of open hearth era casualties. This is not an ideal heritage. It is a factual one. The physical cities, the most direct legacy of the open hearth era, is not a machine or a process. It is geography. The steel that came out of those furnaces is still in service. The structural steel in buildings constructed between 1900 and 1950 is still carrying load. Open hearth steel has a service life measured in centuries when properly maintained. The bridges, the buildings, the infrastructure, it is there. Walk into the older buildings of any major American city. Chicago, New York, Pittsburgh, Cleveland, Detroit. Look at the structural columns, the spandrel beams, the floor framing. Some of that steel was produced in an open hearth furnace at 2,900 degrees by a man standing 8 feet from the open door, working a 12-hour shift, earning $1.25 a day. It is holding up the building you are standing in. The mill buildings are gone, not all of them. A few remain as museums or partial adaptive reuse projects. But the operating mills are gone. The furnaces were decommissioned. The checker chambers were demolished. The buildings were cleared. The cities remain. They changed, but they remain. Chicago is still there. Pittsburgh rebuilt itself. Gary declined this substantially, but it still stands. The cities that steel built were subject to the same economic forces that replaced the technology that built them. The workers are gone. The men who charged the furnaces and read the flame colors and survived the long turns. They lived their lives and died, and the generation that worked those floors has passed. The steel remains. What replaced the open hearth furnace was not a similar machine. It was a more efficient process producing the same material in a fraction of the time. The basic oxygen furnace converted what took 12 hours into 40 minutes. The electric arc furnace eliminated the requirement for integrated steelmaking infrastructure entirely. Both of those technologies are currently operating. American steel production today is conducted primarily in EAF minimills and BAOF integrated facilities. The open hearth furnace is not used anywhere in commercial steel production in the developed world. It did the work it was built to do. For 90 years, it did exactly that, and then it was replaced by something that did the same work better. That is the history of industrial technology. That is the history of every machine that was ever called essential.